Hello, I welcome all of you to lecture number 2 in Valence Bond Theory. Today we will focus on complexes with coordination number 2. I am your friend Dr. Atul Nagpure. I welcome to my chemistry YouTube channel. In today's lecture, we will discuss various characteristics of complexes having coordination number 2, what kinds of metal we require with electronic configuration, and what is the nature of the ligand which generally exhibit coordination number 2. Now if you compare the complexes having coordination number 4 and 6, they are actually common, and metal ion and most of the ligand shows 6 and 4 coordination number. On the other hand, the low coordination number like coordination number 2 are very rare, and that we will discuss. If I take coordination number 2, generally we exhibit that it should always have sp hybridization. That means when metal ion and a ligand react and they give a coordination number 2 complexes, the s and p orbital of the metal ion undergoes process of hybridization and they will give hybrid orbital. This hybrid orbital react with the ligands and they will form the diagonal and linear kind of geometry. This is in this lecture we will discuss various aspects of such kind. Let's say metal ion now wanted to form a linear kind of geometry or diagonal geometry. So the given metal ion or metal atom has s atomic orbital, which will be empty, and p atomic orbital, again this will be empty. So if I take p orbital, we have px, py and pz. For time being, let's consider this is a px atomic orbital. So s atomic orbital and p atomic orbital of metal which is empty now will undergo the process of hybridization, and we will get the two equivalent sp hybrid orbital. You can observe the shape here. The both sp hybrid orbital has equivalent energy and the nearly same shape. So if I take a pure atomic orbital, S is spherical in nature, P pure is a dumbbell shape, and if I compare this pure atomic orbital with the sp hybrid orbital, you will realize that a shape and energy are completely different. Now these two sp hybrid orbital now will arrange themselves in the space and they will adapt a linear kind of geometry or diagonal geometry. So let's take this is my complex. Imagine this is a linear complex, and black is considered now metal ion or metal atom, and these two are the ligand. So if I take angle between in this ligand, this will be 180 angle, and below also we have 180 angle. Such kinds of complexes we known as a linear or diagonal kind of complexes. Now here I have given some example of the complexes which have coordination number 2. This is copper complexes, silver complexes, gold complexes and mercury complexes. Let's take now this a copper complex. Now in these copper complexes we have amine ligand, here we have chloride ligand, and here we have copper plus 1 charge, and here also we have copper plus 1 charge. So now I can say in the both the complexes we have a copper plus 1 charge is the charge on the metal ion, and you know when we have copper plus 1, the system will be always 3d10 system. Okay, am I right? Now here let's take second complexes with coordination number 2, silver, and we have here amine ligand and cyanide ligand. In this case, the silver Ag plus and this Ag plus now have electronic configuration of 4d10. Let's move towards now gold complex. chloride ligand, cyano ligand, and chloride and phosphine ligand. In all the complexes, you might have realized here, gold also has a +1 charge. So I am writing here, in the complex we have a +1 gold, and +1 gold means system will be a 5D10 system. And the last, in mercury complexes, this mercury has the +2 charge. Now you can see very carefully, and this is again a 5D10 system. So copper +1, silver +1, gold +1, and mercury +2 all has the D10 electronic configuration. Now I will just take one complex and we will try to understand how the bonding occur in these kind of complexes having coordination number 2. So now here we have D10 system, and if I want sp hybridization, the empty s orbital and the p orbital of the metal should undergo hybridization. So let's take, we are discussing this copper diamino complex, NH3/2 has a +1 charge, and again writing for your understanding, I have copper +1 and copper +1, nothing but a 3D10 system. Okay, here now I'm writing a D10 or by D10 here, 1, 2, 3, 4, 5. This is nothing but 3D10, and we have 10 electron. So all the orbitals are completely filled. Now what left? We have now 4s orbital. This is 4s orbital. Now this is empty, and we have a 4p orbital. This is also empty. Now when they have sp hybridization, I have already explained with that a pure s atomic orbital and pure p atomic orbital undergo the process of hybridization. This is my px, py, pz. Now I'm writing here below, this is a px and this is py and this is pz. Now consider that empty 4s orbital, one orbital, and one px pure atomic orbital of this metal ion now undergoes the process of hybridization, and this is, they will sp hybridization they are undergoing. And when we have sp hybridization, now I can say that they will arrange in this manner. Okay, this is plus and this is minus and minus and minus. So this is actually sp hybrid orbital. Now I am writing here, this is sp hybrid orbital. Now afterwards, these sp hybrid orbital now react with the ligand, and I am having ligand here, NH3 ligand. So NH3 is now have electron lone pair on the nitrogen, and this nitrogen lone pair will use to form the coordinate kinds of bonds. So I am writing here, this is NH3 we having, and nitrogen has a lone pair, and this 2 star means I am giving a 2 electron, and this is how the ligand gives electron to the hybrid orbital. Again this is 2 star means 2 electron, and we have the NH3 ligand. And here now I can say that I have a copper, and here we have NH3 ligand, and we have here NH3 ligand. And if I take this complexes, the whole charge on the complex will be +1 D10 system, and angle between these two now will have 180 angle, and this is the linear and diagonal kind of complexes. So the same way we can explain the all including copper, silver, gold and mercury. Just for understanding point of view, I explained only one complex. Now if you have sp hybrid orbital, now you know that this lone pair now interact with this. So if I take the bonding, now NH3, the way I shown here, NH3 will react with hybrid metal and they will form these kinds of complexes. Now we'll look whether these complexes are stable. Please keep in mind, when we have small size of ligand, this coordination number 2 are not stable under the given reaction condition, and if they have chances to react, they can form complexes with higher coordination number. So I'm just taking one complex here, silver complex, and we have amine ligand. We have +1 charge. Now we need to understand this coordination number 2, complex with coordination number 2 is stable or not. Now if I react this complex with amine ligand, what they will do? They will try to form a complex with higher coordination number, and this is how they will form the complex with coordination number 4, and this is the reaction. So I'm going to say these complexes are generally not a stable complexes, and if they have a chance to react with some ligand, they will always try to go to form complexes with coordination number of 4. Now I'm just going to explain you why such things happen and what are the nature of the ligand should be have if you wanted to get stable complexes. Now various research study has proved that if we have bulky kinds of ligand, try to stable complexes in coordination number 2. If I compare now with a small ligand, like if I take chloride, cyano and amine, they are a small size of ligand, and when we have coordination number 2 with this small size of ligand, they are not stable. But we can able to obtain a stable complexes if the ligand size is bulky. Now I'm going to explain some ligands of which are the bulkier nature, and this is actually amide kinds of ligand I am giving to you, and this is a silicon derivative. Here we have methyl, and here we have methyl, and again we have methyl. I will remove this part first. So just keep in the mind, the bulky ligand always stabilize the complexes in a low coordination number, and here nitrogen carry a minus charge. Okay, and this complex we generally referred as hexamethyl. Hexamethyl. We have 1, 2, 3, 4, 5, 6 hexamethyl disiloxane. Di means 1, 2 disiloxane, or this is generally referred as HMDS kind of ligand. So this is HMDS. This is also known by different word. We can call also a trimethyl silylamide. This can be known by this thing. So this is actually a bulky ligand, and when we have these kinds of ligand, they can able to stabilize the complex with coordination number 2. So this is complexes. Now they can going to form a stable complexes. I'm just giving some example of such kinds of complexes. Remember that manganese. If I take manganese +2, manganese +2 ion, then we have Fe +2 ion, cobalt +2 ion. Similarly, nickel +2 ion. Along with that, zinc +2 ion, and cadmium +2 ion, and mercury +2 ion. They always form the coordination number 2 complexes with this ligand. So for all this metal ion, I am writing that this is a metal. Yum is metal, and it can be manganese +2, iron +2, cobalt +2, nickel +2, zinc +2, cadmium +2, or mercury +2. So M is metal ion plus 2 charge, and this H, M, D as kinds of ligand, and this is the case. So you know that I am having metal. Metal has a plus 2 charge, and it can be any out of that, and coordination sphere will have 0 charge because each ligand will have here minus 1 charge. So I'm going to say this will be of this kind. Just for example, one example I'm giving to you, HMDS, and we have this kind of, we have 0 charge and zinc as a plus 2 charge. So not only these, we have various kinds of ligands of this type. So now this is HMDS. Now imagine if I replace 2-methyl from the silyl group, and if I write down here phenyl group, this is also a bulkier ligand and which will able to stabilize the complex with coordination number 2. Similarly, we may have the boryl group. Boryl group means this is xylene and carry a minus charge, and here again we have here boron and MEs, and this is again MEs. For information, this xylene nothing but a dimethylbenzene. Remember that dimethylbenzene, and this MEs nothing but mesitylene. Mesitylene means a trimethylbenzene. So this bulkier group now can be able to stabilize the complexes. One thing you have to keep in mind here, this boryl group is very important here, because this boryl group, what it will do, it will try to stabilize the complexes in a different manner. So if you have nitrogen and boron linkage, this boron will try to take electron density from the nitrogen via pi bonding, and this is now a pi bonding occur, and hence this nitrogen will not going to form a bridge. So monomeric kinds of complexes we can able to get if you have boryl kind of group at the nitrogen center. So I mean to say, when we have this boryl group, now they will going to take electron density from the nitrogen, and electron density at nitrogen now get decreased, and that's how they will not going to form bridge kinds of complexes. Now further, now question is there, how we can able to understand whether these are monomeric or dimeric species. Just giving some example here. If we have a manganese HMDS, hexamethyl disilyazine complex, and I'm having now 0 charge. Similarly, a cobalt HMDS complex, now this is a 0. Now both of the complex, now if I ask you, are they monomeric or they are dimeric in state? So firstly, when you are discussing any complex, the physical state, liquid state, gaseous state, or the crystalline state, that you should know very carefully, because if I take both the complex and if I discuss in the gaseous phase, this will be in a monomeric form. Monomeric, and if I discuss in a crystalline state, this will be in a dimeric form. So prior knowledge of the phase of the compound is very essential if you wanted to understand dimeric, trimeric or tetrameric nature of the given complexes. I'm going to ask you one question on that respect. Say I have this complex, copper cyanide complex. Okay, this is my complex. Now question is, what is the coordination number of this complex? most of you, I know that you will say, sir, we have cyanide, we have two cyanides ion, and in this complex we have copper plus 1. So you will say that, sir, this is a coordination number 2 complex. But actually this is wrong. Why wrong? Because in a crystalline state, this complex is actually has the polymeric nature and is a polymer kind of things, and we have cyanide and we have copper and Cn, and again we have cyanide and again we have copper CuCN, and so on. So this is what polymer kinds of chain discussing the same thing, and this is first, second and third. So this complex maybe look like coordination number 2, but this is not the case. This is a coordination number 3 complex. This is the way you need to observe the chemistry properly. You can't take a simple decision based only on the their molecular formula. Structure of the complexes is very essential if you want to conclude the coordination number and nature of the complexes. Now, one interesting part I'm going to discuss here. Most of you know that complexes with coordination number 2 is having always sp hybridization. This is known for all of you. sp when we have coordination number 2. But do we have hybridization except coordination number 2? Let's take we have complexes of this type, RuCl2 and RuBr2 and RuIride2. This is complexes of the ruthenium with having Ru in a +2 state, and we have halide as a ligand. Now in this case, please keep in the mind, when n-1d level has the equivalent energy with ns and np atomic orbital, what happened? Now this d orbital can takes part in the bonding, and you may have, remember, sd kind of hybridization, and this is the new concept you might have be coming across, sd kind of hybridization. And in this, it is possible that if d orbital has the equivalent energy, it can take part in the bonding and it can have sd hybridization. The link of this I will give in a description box, so you can